Okay, so this is a kind of okay, so this is a representation category, and it is certainly an abelian category, but it is more than an abelian category. We want to get some interesting information. For example, if we want to get some not invariant or some other invariant in three-dimensional topology, then you want to put a tensor structure on the representation category. So, and in order to put this tensor category, to put a tensor, the monoidal structure or the tensor category structure on this category, we want the crucial step is to study the conformal blocks. So conformal block is the main one of the main the central top the object in our talk. So one of the main reasons for studying conformal blocks is to put a tensor structure and study some properties satisfied by this representation category. Okay. So this is the untwisted or non-orbifold story. So what about the twisted story? What about the orbifold conformal theory? So I'm going to point out the difference. The main difference is that now we have a group, and many people will focus on the finite group, because we already have many interesting phenomenon if you look at the finite group of automorphisms on the VOA. And here I'm going to use the U to denote a one with a automorphism. And so roughly speaking, when we study the orbifold theory, so many things could be reduced to study the representation category of the fixed points of algebra. So the meaning is clear. You take the fixed points of algebra and you study the representation category, right? So the goal is very similar to the untwisted part. But the difficulty is that because we have a finite group, you have some automorphisms, then it will give you some more extra data. And one important problem in the orbifold theory is to study the relations between the twisted part and the untwisted part. And here's one important thing is that if you only study the untwisted part, then you cannot get all the information from the representation category of the fixed points of algebras. You will so many things are not so many information in this category cannot be recovered from the original category of the bigger VOA. And so if we want to study these fixed points of algebra, we have to study something outside this category. So mainly we want to study the category of twisted representations. So the philosophy is this: we want to reduce the study of the rep UG to the study of the VOA U. But if you only focus on the ordinary representations, you cannot get all the information for the rep or UG. So in order to study UG by studying U, we have to extend our definition of the representations. We have to study not just these kind of ordinary representations, ordinary modules. We also should study these so-called G-twisted representations. And there are indeed some general theorems that guarantees that well, if your VOA satisfies some natural conditions, then these two categories are you can go from one side to the other side and vice versa. Okay, and there are some and these theorems are mainly due to Kirillov-Milgan and more recently by Robert McRae. So that's why we are interested in twisted modules, because we need twisted modules to study the representation of the fixed points of algebra. Okay, so this is a very quick introduction to the orbifold conformal field theory. Okay, let's see. Okay, now I want to talk about the permutation orbifold conformal field theory. What is special about orbifold conformal field theory is that, well, roughly speaking, we only need to start. I mean, all the twisted part could be more or less recovered from the untwisted part. But and we have to be careful that I'm not talking about the untwisted U modules. I'm talking about the untwisted, all the untwisted V modules. So we can so the thing is this, we take U to be a finite tensor product of V, and here I'm writing this in a more or less coordinate independent way, which I mean is that I use the general set E, a finite set, and take the tensor product. So if E has n elements, then this is just a n tensor product of V. So this is nothing special. And here the automorphism group I'm thinking about is just the permutations. You can take G to be the full permutation group of this finite set. You can also take it to be a subset of this this permutation group or the automorphism group. Then this group acts on the VOA U by permutation, by permuting each components, each tensor component. So you can define this group action in a very obvious way. And I'm interested. So the permutation orbifold theory is the study of this type of conformal field theory. And for this type of conformal field theory, we have a so-called twisted and untwisted correspondence. And this is the main thing that I'm going to talk about today. So the correspondence says that the G twisted V tensor E modules and their conformal blocks can be constructed from the untwisted V modules and conformal blocks, and actually vice versa in some cases. And moreover, actually conformal blocks are not just associated to the VOAs and their representations. They are also associated to the Riemann surfaces, because conformal field theory deals with conformal field theories are actually kind of conformal field theories on the Riemann surfaces. So we have to, so these two data also depend on the Riemann surfaces, and there are actually some relations between the Riemann surface for the twisted part and the Riemann surface for the untwisted part. Well, to be more precise, the Riemann surface for the untwisted part is a branched covering of the Riemann surface on the twisted part. Okay, so this is roughly speaking what this correspondence is, and I will say more details about these things later. Okay. Do you have any questions? Okay. Okay. So I will what I will do next is to explain the meanings of the names that I have mentioned previously. First of all, I'm going to tell you what are twisted modules. The best way to show you what are twisted modules is to compare twisted modules with untwisted modules. So what are the main difference between twisted modules and untwisted modules? So roughly speaking, twisted modules are the modules with kind of monodromies. So let's just first recall some basic facts about the untwisted modules. So untwisted modules, so if you have a VOA, so V, and so you have a vertex operator, right? So the vertex operator itself acts on V. So for each vector small u inside this vector space V, and you get this field operator. This field operator is acting on V itself. Okay, if you care about the rigorous things, then actually it is not a linear operator on V. It is a linear map from V to a so-called algebraic closure. But if you can, so for the purpose of our talk, we can ignore this subtlety. You can just think about this field operator as acting on V. So this is a field operator which depends. First of all, it depends linearly on U. This is very natural, but also it depends holomorphically on Z. So Z is a complex variable variable defined on the punctured complex plane. It cannot be defined on the origin, so it is defined on the punctured complex plane holomorphically. And so these field operators satisfy some axioms, the so-called Jacobi identity. So this formula should be understood in the sense of complex analytic continuation. So I'm not going to talk about the details, because if you want to care about details, then I will need many time to say this. So I will so don't worry about the details of this Jacobi identity if you are not familiar with this. So the main thing is that, first of all, so this vertex operator is acting on V, but you can also let this vertex operator act on any V module. Actually, V module is defined just by this kind of vertex operator satisfying some axioms that are also satisfied by the original vertex operator. So here, if I add the subscript W to Y, it means that now the vertex operator is not acting on V, but is acting on a V module W. So this is W is a part of a different vector space, and of course V itself is also a V module. And here's the important thing. Here's one important thing is that for untwisted modules, these are also holomorphic functions of Z defined on the punctured complex plane. But in contrast, when we think about the G-twisted modules, then this vertex operator, well, it is still a analytic with respect to Z, but here this vertex operator is not a single valued function of Z. It is multi-valued. There is a kind of monodromy, and the monodromy is controlled by an element of G. So actually, when we talk about G-twisted modules, we have to we have to choose an element small g inside the group big G, and we talk about the small g twisted module. A small g twisted module is, roughly speaking, a twisted module whose monodromy with respect to Z is controlled by this small g. Okay, so now Z is so Y is multi-valued with respect to Z, but if you take some square root, then it is single valued with respect to some fractional power of Z. And if you move Z around the origin, the argument of the Z will okay, if you move clockwise, then the argument will decrease by 2 pi, and this 2 pi is contributed by the action of G. So this is the main difference. This is the formula that points out the main difference between G-twisted modules and untwisted modules. Okay, so this is, roughly speaking, what are twisted modules. Okay. Let me give you an example, which is also quite related to the subject of our talk today. I will give you an example of how to construct twisted modules for permutation orbifold theory from untwisted modules, and this construction is due to Baron Mason. So this is the algebraic definition. So recall that our VOA now is a finite tensor product of V, and we have G is a permutation. So let us first consider the easy case, that is E is a finite set consisting of k elements, and G is a cycle of k elements. So G has only one orbit. Okay, so G acts transitively on this set. So now G has only one orbit, and we can define. So let us choose this W to be a V module, and we can then on this same vector space, we can define a G-twisted module structure on V tensor E. Okay, so these two W are equal as vector spaces, but they are not equal as modules. So this is the V module, and this is the G-twisted V tensor E module. Okay, so on the right hand side, this is the vertex operator for W, and on the left hand side, this is a twisted vertex operator for this W. And these two vertex operators are related by this formula. So roughly speaking, on the left hand side, this is the vertex operator from a tensor product of vectors inside V. Okay, and you define this vertex operator to be some product of the untwisted vertex operators for V, for the original V, and each tensor component appears in one vertex operator. But this part, it means that different tensor components, because if we want to take the case root of Z, and there are k different case roots, and for each case root, I assign it to one vertex operator. So this is the algebraic definition, and here is a modular explanation. On the right hand side, this is the picture for the twisted part. So for the twisted part, the vertex operator. This vertex operator acting on a vector W. Oh, sorry, this strip is small w here. Okay, this outgoing vector is this operator acting on this small w. So this what vector is you get is intuitively it just means that okay, on this sphere at the origin you put in a vector w, and at the z puncture you put in this tensor product. So you put in these two vectors, and the outgoing vector you get is the vertex operator acting on this small vector. Okay, this is the right-hand side. And it could be, so this is the twisted part. It could be recovered from the untwisted part by, okay, so now here, these K elements are the case, all the case roots of the Z. And for each root, you put all these tensor components to here, and then the outgoing vector is the same as the outgoing vector here. So this is the geometric explanation. Okay, and from this geometric explanation, you can actually I would say that this picture is also a prototype of our twisted correspondence. You can see that the Riemann surface here is a branched covering. It is a k-fold branched covering of the right-hand side. Right? Outside 0 and infinity, this is just the ordinary covering space. But at the origin and infinite point, this is these two points are the branch points. Okay, and outside the branch point, this is just an ordinary covering map. Okay, so this is a very simple example of the twisted and untwisted correspondence, and an easy example of the branch covering. And the general case will involve more complicated branch coverings, which I will talk about later in my talk today. Okay, and next I will slightly generalize what I said, generalize the previous example, because in the previous example, the element G is acting transitively on the finite set, which means that we only have one orbit, right? But what if we have several orbits? Well, the generalization is very straightforward. We just need to, for each orbit, you define the twisted vertex operator in this way, and you multiply them. Okay, you multiply them, then you get the twisted vertex operator for the whole whole V tensor E. Okay, so the general case is very straightforward. Okay, so this is an example of constructing this permutation twisted modules. Okay, and it is not difficult to verify that. Use this picture to verify that it satisfies the monodromy property, because if you move this Z by 2 pi, it means that here you move it by 2 pi over k, and then this means that you don't move, you fix these points, but you move the vectors, right? You move the vectors, it just means that you permutate the vector. So this shows that the monodromy, that moving Z by 2 pi is equivalent to moving the vectors, which is the same as permuting the vectors, right? So this satisfies the definition of the twisted modules. Okay, so this is an example of the twisted modules. Okay. Okay, so next I will say I will show you some brief history of this correspondence. Okay, and certainly this is not a complete history. I will so I will begin with the physical story. So to my knowledge, the first this kind of correspondence was first realized by physicist Bante in around 2000. In his paper, Bante wrote 2 papers on the permutation orbifolds, and in those papers, he pointed out this correspondence. In particular, he pointed out that the Riemann surface on the twisted side should correspond to a branched covering of the Riemann surface on the untwisted side. But in Bante's paper, he mainly focused on the unbranched coverings, which means that these are just the ordinary covering spaces. Okay, so this means that Bante didn't actually explicitly constructed all these branched coverings which are crucial to this correspondence. Okay, so this is physics, and the next progress, to my knowledge, the next progress is on the conformal net side, which is a functional analytic approach to the conformal field theory. So the story is this: in 2001, Kawai, Higoshi, Long, and Muger, they wrote a paper to study the so-called complete rationality. So complete rationality is a rigorous way to formalize the rational phenomena in the physics literature of conformal field theory. Okay, so this is a mathematical rigorous way to study the rationality. Okay, and to my opinion, this is one of the most important papers in the literature of conformal nets. And in that paper, these three authors, they study the complete rationality and also the modularity of this representation category using the Z2 permutation orbifold conformal field theory. Okay. So how are their work related to the correspondence? So actually their work raises a very interesting question. It is that the modularity is about genus one property of the conformal field theory, because you studied S matrix, which are related to the modular properties, the modular space of genus one surfaces, right? So it is a genus one property, but conformal nets seems to be only applicable to the only genus zero conformal field theory, because conformal nets they are basically just a net a class of algebras associated to the circle. So conformal nets are basically only genus zero stuff, but surprisingly they can use the genus zero stuff to study the genus one property, like the modularity, the S matrix. So why they study this genus one property by using this Z2 permutation conformal field theory. Okay, so and a retrospective explanation of this story is this: is why they can use the genus zero permutation orbifold to study genus one property is this. From the point of view of twisted and untwisted correspondence, the genus zero part, well, on the twisted side, if you choose a genus zero surface, then on the untwisted side, you have to choose a branched covering, right? And this branched covering will be higher genus. And in particular, if you take the Z2 permutation, you will get the genus one. Okay, so this is a very rough explanation of why in this paper, these three authors could use genus zero stuff to study the genus one stuff. Okay. Next, so let me mention some later works on these conformal nets. These are some later progress on this on the study of this correspondence in the conformal net picture. They involve Longo and Chiffon and class Longo and Chiffon, and actually more recently by Zhenwei and Chiffon. And I want to make some remarks on the second work. The second work, they actually computed some fusion rules for permutation-twisted modules. Okay, but their calculations only restrict to the cyclic cases. And actually, to my knowledge, even the cyclic case is not complete. In that paper, there are some words which says that there should be some geometric explanation, some more natural explanation of this correspondence, because in their computation they already realized that their computation of twisted fusion rules are equal to some fusion rules of the higher genus and twisted rules. They noticed this phenomena by explicitly calculating the fusion rules, but that paper could not explain this. They could not give this geometric explanation. Okay, so this is what this paper do. Okay, so next let me turn to the VOA side. Okay, so the first is the Barrington-Mason, which I have previously mentioned, and the Barrington-Mason Barrington-Mason's work only focused on the twisted modules, but not conformal blocks, which means that they only consider modules but do not compute the fusion rules. Actually, the computation of fusion rules are quite recent in 2021 by Dongxi and Yu. And sorry, this work is also for the modules, but this work in 2019 are they study the fusion rules among the cyclic cases, which means that these are all both works are focusing on the abelian cases. And even in the cyclic case, the abelian case, the Zn case, the computation, to my knowledge, it is not complete. Okay, oops. So next, these are some approach to this correspondence from the point of view of tensor category. And in this tensor category approach, the computation of fusion rules are more complete than the previous approaches. but these approaches have some limitations. The limitation is that although the calculation of fusion rules in this tensor category framework are more complete than the previous ones, we cannot directly apply this tensor category result to the previous result, because in this tensor category framework, what they do is that they characterize the fusion rings in a very abstract way, but they do not show how to identify the objects in the fusion rings with the objects that we can explicitly construct in either the VOA context or the conformal context. For example, we cannot identify these abstract objects in the fusion rings with the twisted modules in the, let's say, the Barrington-Mason's construction. So this means that we cannot directly apply the result to the explicit VOA or the conformal context, which means that if you are given 3 explicitly constructed permutation-twisted modules, let's say you constructed from using the Barrington-Mason's method, you cannot use this method to directly show that their fusion rules are blah blah blah. Certainly, these rules give you they show that they give you suggestion, they give you hints on how the fusion rules look like, but you cannot use them to prove that. They do not prove that for explicit construct twisted modules the fusion rules are like that. Are like that. Okay, so these are the limitations of this kind of tensor categorical approach. And one last word about this approach is that among these works, the work by Baumeier-Schweigert is most closely to the approach that I take into this talk. Actually, they construct the topological branch coverings. Okay, so they study this correspondence in a quite complete, quite systematic way, but they focus on the topological part. So it means that if we want to study the correspondence in the VOA context, we have to put complex analytic structures on these branch coverings. We have to extend the Baumeier-Schweigert's words to the complex analytic category. Okay. Okay, so these are some brief histories. And next, I want to tell you what are conformal blocks. Okay, I want to show you some elementary properties, give you some rough ideas about what are conformal blocks. So to talk about conformal block, we have to first choose a Riemann surface. So in my talk, Riemann surface always means compact Riemann surfaces. Okay, and there are endpoints. So these are the marked points. You can also think about these as punctures. So for each point, you put in some vectors, right? You put in some vectors and you get something. Okay, and for each marked point, I also associate a local coordinate. So local coordinate just means that it is a holomorphic function from a neighborhood. For example, eta1 is a holomorphic function from a neighborhood of x1 to a neighborhood of 0 inside the complex plane. This is an injective map, and it sends x1 to it sends the mark point to 0. Okay, in other words, this local coordinate it identifies a neighborhood of x1 with a neighborhood of 0 in a analytic way. Okay, so this I call this to be an endpointed Riemann surface with local coordinates. Okay, and a conformal block. Okay, also for each mark point, we need to associate a V module. Okay, and a conformal block is a linear functional on the tensor product of all these V modules. This is a linear product, which this is a linear functional which satisfies some covariance properties. Okay, so this is the picture. So roughly speaking, a conformal block is just a linear function, right? So you put in some vectors. So W1 is a vector inside the big W1, the module big W1, because the big W1 is the module associated to X1, right? And you put in all the vectors, and what you get is a number, right? So this is the machinery given by the conformal block, and this conformal block should satisfy some covariance property. And actually, the details about this. So the rigorous statement of this covariance property is very complicated, but roughly speaking, this covariance property should be understood in the sense of analytic continuation. So roughly speaking, this covariance property says this. It says that, okay, at each W1, for example, at WI, you can let the vertex operator, you can choose a small v inside the vector space, the vertex operator v, the big V, and you can let this vertex operator acting on W, right? This means that you let the small v acting you let the small v first interact with this W1. You get a new vector, which is this vector, and then you let this vector to engage in this interaction of this of this Riemann surface, right? And then you get a number. Okay, the covariance property says that all these, well, because at each point you can define this operator, right? And these definitions are compatible, which means that their analytic continuation are the same. Okay, so roughly speaking, this covariance property should be understood in the sense of the analytic continuation. Okay, they could be analytically extended to the same meromorphic section with poles at this mark point, at these mark points. Okay, so this is a rough definition of the conformal blocks, and I want to point out a difference. So here I'm talking about conformal blocks for untwisted modules. For twisted modules, this definition does not work. I will talk about I will give you more details about conformal blocks for twisted modules later. But for the moment, I want to point out one very important difference between untwisted conformal blocks and twisted conformal blocks. For the twisted conformal blocks, if you associate twisted modules to these mark points, you cannot extend this expression to the same meromorphic function. Because as I said, you will have, if you add this vertex operator associated to a twisted modules, then you will have monodromy, right? Which means that if you put it here, if you let this function move around this mark point by 2 pi, then you will get a different number, right? You will get monodromy here. You will not get a single valued function even on a punctured neighborhood of mark points. So let alone on this whole Riemann surface. So for twisted modules, for twisted conformal blocks, you will never extend these expressions to the same meromorphic functions. You have to consider the multi-valued meromorphic functions. Okay, so this is one important difference between untwisted conformal blocks and twisted conformal blocks. And I will say more about the twisted conformal blocks later. Okay, so these are the rough explanations of what are the conformal blocks for the untwisted modules. Okay. And let me mention some very important properties about the conformal blocks. Okay, so if you know a little bit about the modal functors, then conformal blocks, they just correspond to the modal functors. Okay, so they satisfy some properties that modal functors should satisfy. For example, we expect that the dimension of conformal blocks should be finite dimensional. Also, and certainly for this condition to be true, we have to add some conditions on the VOAs. Okay, and these are some very natural, some well-known conditions for vertex operator algebras. But if you don't know this, you can ignore this. You can just focus on the properties. Okay. So the first is the finite dimensional, and also this dimension. This is actually the fusion rules, but not necessarily the fusion rules for because the usual fusion rules are for the Riemann spheres for three punctures, 3 mark points, and actually for any Riemann surface, n-pointed Riemann surface, you can define this dimension. So this is a possibly higher genus fusion rules. And this dimension, it does not depend on the complex structure of C. And it also does not depend on the local coordinates and the location. So basically, it just says that this dimension is a topological information. Okay, it is not a complex analytic information. Okay, so this is one thing. This means that we can understand conformal field theory from a topological point of view. Okay, so this is the importance of this first property. The second property is called a sewing. The sewing is, roughly speaking, is like this. So suppose that W1 is the dual representation of W2. In particular, these two vector spaces are dual spaces of each other, and then you can take the contraction. Okay, you take a contraction. So for the original conformal block, you take a contraction, you get a new linear functional, and this new linear functional is also a conformal block, but it is not a conformal block for the original pointed Riemann surface. It is a conformal block for a new Riemann surface. The new Riemann surface is the sewing of the original one. So for example, for this picture, you have 4 mark points. So the original conformal block is a linear functional on the tensor product of 4 modules. And after you take the contraction, you get the linear function on the tensor product of only 2 modules. That is W3 tensor W4, right? And these two are, you take the contraction, right? You take the contraction, and then this contraction give you a conformal block for the right-hand side, for the sewing. Okay, so taking roughly speaking, taking contraction correspond to taking the sewing, correspond geometrically to taking the sewing of the Riemann surfaces. Okay, so for that reason, we also call this algebraic process to be the sewing of the original conformal block. So contraction are also called the sewing. Okay, so there are 2 types of the sewing. The first one is the self-sewing. The second one is the disjoint sewing. Okay, so this is the second important property, the sewing property. And the last important property is kind of the opposite of the sewing property. It is called the factorization. So roughly speaking, factorization says that any conformal block on the right-hand side could be written as the sewing of the conformal block on the left-hand side. Okay, it says that the sewing process will give you enough conformal blocks on these possibly homogeneous Riemann surfaces. Okay, so this is called the factorization. Okay, actually the sewing and factorization, these properties are one of the most important property in rational conformal field theory. For example, the associativity isomorphisms in the representation category of VOA is a special case of the sewing factorization. And also model invariance is also a special case. So this is the genus 0 sewing factorization, and model invariance is the genus 1 sewing factorization. Okay, and also a slightly different version of the factorization is this formula. Okay, it tells you that the dimension of the space of conformal blocks on the right-hand side could be computed by the dimension of the space of conformal blocks by the left-hand side. Okay, you just the right-hand side dimension is just the left-hand dimension where you take the sum over all irreducible modules up to equivalence, all different irreducible modules up to equivalence. So here, for the first mark point, you put W1, then for the second mark point, you should put the 0 module. Okay, so it means that you can compute the dimension of the space of conformal blocks for higher genus Riemann surfaces to using the data for the lower genus dimension of the lower genus conformal blocks, and ultimately all these dimensions of conformal blocks, spaces of conformal blocks, could be reduced to the computation of the fusion rules, namely the dimensions of the spaces of conformal blocks associated to 3 point spheres. Okay, so this is an important the importance of the factorization. It gives you a reductive formula to compute all the dimensions for the space of conformal blocks. Okay, so these are about the sewing and factorization. Okay, any questions? Okay, so next, let me return to let me go to the twisted words. Okay, I will tell you what are the main ingredients in the twisted conformal blocks. I will mainly focus on the genus 0 case, but it also generalized in a very straightforward ways to higher genus case. So for the genus 0 case, the problem is how to define twisted conformal blocks. Okay, it turns out that as I said previously, we have to include multi-valued holomorphic functions in order to study conformal blocks. Okay, so because we have this multi-valued property, it turns out that the data to get a unique data, only pointed Riemann surfaces are not enough. We also have to add the paths. Okay, the paths controls the monodromies. They fix the initial monodromies. For example, it will turn out that if you take different homotopic classes of paths, then the conformal blocks you get will be different. Okay, so here are some details. I will call this data to be an n-pass sphere. This means that you have a sphere, you have n distinct mark points. At each mark point, you have local coordinate eta. But besides the mark points and local coordinates, I also have a path. Okay, the path is going from a point which is close to the mark, close but not equal to the mark points, to a common endpoint. Okay, so these blue paths, these blue curves are the paths. Okay, I need a path to define the twisted conformal blocks, and it turns out that this definition depends on the homotopy classes of these paths. Okay, and I also want to define this alpha I. So what is this alpha I? You choose this small anti-clockwise circle around the mark point xi, and then the alpha I is the path which goes like this. You go, the first step is here, the second step is here, and the last step is here. So the alpha I is a path from and to the fixed mark point star. Okay, so in other words, all these alpha I could be understood as elements of the fundamental group. Okay, and this fundamental group is crucial for our study of the permutation twisted conformal blocks. Okay, so these are some basic geometric setting. Okay, and now I'm based on this geometric setting, I will define the conformal blocks. Give you the rough definition of the conformal block. Certainly, for each mark point, I'm going to associate the twisted modules. More precisely, for each mark point xi, I will choose a GI twisted module. So this means that GI, so recall that each GI is a group element, right? We have a big G, we have a big group, big G, acting as an automorphism on the VOAU, right? And for each I, you choose a group element GI, okay? And you choose a GI twisted U module WI, which means that the monodromy of WI, when you move this around this circle, around the mark point, this monodromy is reflected by the action of this small group GI, right? This is because this is the definition of the GI twisted module, right? Okay, and then I define again the conformal block associated to all these modules and this data to be a linear functional. Okay, and this linear functional should also satisfy certain covariance property. The covariance is this. Okay, first of all, there's one thing that I forgot to mention in the previous page, but let me point out this. I'm going to assume that this initial point is sent to a positive number by the local coordinate. Right? It means that if you take eta I, then the value of eta I at this initial point is a positive number. I fix this in positive so that I can choose the argument to be 0. Because if our argument is 0, then it will simplify some of the discussions. Okay, so but anyway, this is not a very essential assumption. The important thing is that what is that covariance property for in the definition of conformal block? The covariance property is this. First of all, recall that you can let this vertex operator acting on each WI. This means that you can let the vector U inside big U first interact with each WI, and then you let the outgoing vector to interact with the remaining vectors, right? And the covariance property is this. It says that first all these expressions could be extended to a holomorphic function on a neighborhood of the blue paths, a neighborhood of all these gammas. Okay, and this extension is single valued, and then we can also extend this holomorphic function furthermore to a multi-valued function on the sphere outside this mark point. Okay, this is not a meromorphic function because the poles will have fractional powers. I will prefer not to say this to be a meromorphic function. But anyway, outside the points, outside this mark point, this can be extended to a multi-valued section. Okay, so this is the modification we need in order to define the twisted conformal blocks. Okay. Okay, so next I will return to the setting of permutation orbifold conformal field theory, and then I will show you the main result. So we return to the setting that U is a tensor product indexed by E of the same VOA V, and G is a finite subgroup of the full automorphism group. For example, you can just take G to be the full permutation group. Okay, and for each I take a group element, and for the GI, I take a GI twisted V tensor E module. I constructed from the Barrington-Mason construction. And by the way, the Barrington-Mason construction will give you all the twisted modules when the VOA is rational. When the VOA is not rational, then the Barrington-Mason construction is not enough. Okay. And record that. So this means that this Wi is a tensor product of V modules. Recall previously when we discussed the Barrington-Mason, we said that when we have only one orbit, if GI has only one orbit, then Wi is just a module of V. Right? If you have several different orbits, then the number of orbits is the same. For each orbit, I choose a V module, and on this same vector space, I introduce a twisted structure. Right. So the number of tensor components is the same as the number of the GI orbits. For each GI orbit, I choose a V module, and on the which is called the WIO, and on this vector space, I can have a twisted vertex operator, and this twisted vertex operator, you tensor together, you get a twisted vertex operator on the whole tensor product space. Okay, so roughly speaking, the key point is that each orbit corresponds to each V module, and all these V modules tensor together has a structure of GI twisted V tensor E module. Okay, so this is our recall of the key points of the Barrington-Mason construction. I recall this because this point is quite important for the twisted and untwisted correspondence. Okay, and next, this is the main result. The main result says that, okay, these two vector spaces are the same, right? You have a same vector space. It could be regarded as a tensor product of V modules. You can also, but I would say that this is either a tensor product of U twisted modules, and it is also a tensor product of V modules. So you can talk about whether this is a so if you choose a linear functional on this vector space, and then we can talk about whether this linear functional of the twisted conformal block for U. You can also talk about whether this is a conformal block for the V modules. And it turns out that these two notions are the same. A linear functional is a twisted conformal block, is a conformal block for W1 to Wn, and the previously chosen geometric data P, if and only if the same linear functional is a conformal block associated to all these V modules in a pointed compact Riemann surface X. This X is actually a branched covering of the Riemann sphere. And in the next several pages, I will explain what is this branched covering. Okay. And also note that these V modules correspond bidirectly to the marked points of X. Okay, and actually the marked points of X are precisely the inverse image of the marked points of P under the branched covering. Okay, so next I will show you what is this branched covering. What is the Riemann surface associated to the untwisted part? Okay, the twisted part, the Riemann surface is just a sphere with paths. On the right-hand side, I'm going to show you what are these Riemann surfaces. To describe what is this Riemann surface, what is this branched covering, I will first need to recall this quite basic fact about the covering space, which you certainly have learned if you have taken the very first course in Eurythmic topology. So recall that if Y is a connected manifold, you fix a marked point star, and the finite connected covering spaces of Y correspond bidirectly to the cofinite subgroups. The cofinite condition corresponds to the finite condition. If you remove the finite condition, then you remove the cofinite condition. Okay. Anyway, the covering spaces, connected covering spaces, correspond bijectively to subgroups of the fundamental group. Right? And this subgroup also corresponds to the transitive action, which means that actions with only one orbit. You just take the action on the coset, right? You get the transitive action. So this is clear. Okay. And for our theorem, we also need to consider disconnected covering spaces. And correspondingly, we have to consider general actions on finite sets, which has possibly more than one orbit. Okay, in that case, each orbit corresponds to one connected component of the covering map. Okay, so the correspondence is very easy. So you just put all of them together, then the finite covering spaces correspond bijectively to the actions of the fundamental group on a finite set E, and the connected components of X correspond bijectively to the orbits of the fundamental group. Okay, so in other words, if you have two orbits, then you have two connected components. Okay, so this is the general thing we need to recall in order to define the branched covering. Recall that here this covering is not branched. This is for the unbranched covering, but I will talk about but in that theorem it is the branched covering. But if you go outside, if you restrict out, if you focus on the outside part of the mark points, then you will get the unbranched covering, the usual branched covering. Okay, so here this is the description for the branched covering. The description is this. So first of all, as I said, the mark points for the branched covering is precisely the inverse image of the mark points of the Riemann sphere, which is the geometric data on the twisted side. Okay, and here the branched covering, because as I said, outside the mark points, it is unbranched. This is the unbranched covering, and this unbranched covering could be described by an action of the fundamental group on the finite set E. And here is how to describe it. It is described by sending each alpha I. Recall that alpha I is an element of this fundamental group. Okay, I define the action of gamma on E by sending each alpha I to Gi. Okay, and this definition has some subtleties. So first of all, I have to assume that all these alpha I generate this fundamental group. Okay, in many common cases this is true, but in some weird cases this is not true. I want to, for example, if you let this curve go in a very weird way, then these loops around all the mark points might not always generate the finite group. But in this, for example, in the picture, in this picture, you see these elements certainly generate the fundamental group. So this is the first thing. The second thing is that even if these elements generate the fundamental group, you might not necessarily be able to define the action of G, because you have to, in order to define, because all these elements inside the fundamental groups, these are not free elements. These do not generate freely this fundamental group. For example, in this picture, the paths alpha 1 and alpha 2 are free generators. But alpha 3, if you add alpha 3, then alpha 3, the loop here, could be expressed as the product of alpha 1 and alpha 2. And in that case, G3 should be, well, I should say that in this case, alpha 1 times alpha 2 times alpha 3 should be the identity. And in that case, we have to assume that G1 times G2 times G3 is equal to identity. If they were not identity, then we understood the conformal blocks to be 0. Okay, so these are the necessary requirements. Okay, and then if these requirements are satisfied, then we can define the action of the fundamental group on the finite set E, and this action determines a covering space of the sphere with the mark points removed, and this these unbranched coverings outside the marked points could be extended to a branched covering on the compact Riemann surface. So this unbranched covering could be extended in a unique way to a branched covering from C to C to P1. Okay, so this actually uniquely describes the branched covering. Okay, so this is how we construct this branched covering. Okay. And the way we associate the modules to the marked points is more complicated, so I will not talk about this today. I want to talk about this quite well-known fact. That is, we can the genus of the branch covering. Well, I should say that the genus of each connected component of the branch covering could be explicitly calculated using the Riemann-Hurwitz formula. So once you know the genus, you can use the factorization formula to reduce the dimension of the high genus untwisted conformal blocks to the genus 0 to the fusion rules. So the logic is this: the theorem relates the untwisted conformal block with the twisted conformal blocks, right? Our goal is to, for example, calculate the fusion rule for the twisted part. And this theorem shows that the twisted part fusion rules could be is the same as the fusion rules for the untwisted part, but the fusion rules for the untwisted part might be higher genus. But the genus could be explicitly calculated using this formula. And once you know the genus, you can then use the factorization property to reduce it to the ordinary fusion rules for genus 0, 3 mark points data. So all these twisted fusion rules permutation fusion rules could be explicitly calculated in terms of the ordinary, which means that genus 0, 3 mark points fusion rules for the untwisted V modules. Okay, so this is a immediate consequence of our main theorem. And here is, let me close my talk by giving you this example. That is, if you choose P to have 4 mark points, 0, A, B, and infinity, and you consider the Z2 permutation orbifold. That is, you have the generator acting, you're permuting 2 elements. So in this case, E, the finite set E has only 2 elements. Okay, and for each mark point, I associate the sigma twisted module, which means that you pick a V module, and this V module is automatically a sigma twisted V tensor V module according to the Barrington-Mason construction. And then about this data, we can talk about the conformal block. For the twisted conformal block, the corresponding untwisted conformal block, the branched covering is the elliptic curve. So in particular, it has genus 1. Okay, so in this case, this branched covering could be explicitly constructed. Okay, so that's all for my talk.